Now, because of tautomerization, there's an additional reaction we can run that's kind of unique to what are called, they're unique to ketones that have a methyl group. Now, to run this reaction, ideally we would have an R group over here which does not have a hydrogen on it. So that alpha carbon to the left in this image doesn't have a hydrogen because we don't want it to undergo substitutions. Now that said, it can, but it needs to be an alpha carbon that isn't purely hydrogens around it. It's not a CH3 group. So it needs to be a carbon that's either has no hydrogens or it's not completely saturated with hydrogens. What's going to happen? Well, if I wrote this reaction and said, okay, assume this doesn't participate, what do you get? What would be your expectation now that you've looked at these videos on enols and enolates? And hopefully what you're saying is that, well, I would get substitution. And you would be correct. We would get the initial mono substitution with a halogen, but let's say we run underneath an excess of H2. So we run the reaction again with more X2. What happens? Well, we created HX. That's going to catalyze the reaction, so we're going to get a second substitution. And let's say I dump even more X2 into the reactor. So what we've done here is that we've removed all the hydrogens off of that methyl alpha carbon. Now, this on its own is not particularly interesting. This is what you expect, but here's the interesting trick. Let's now add a nucleophile, particularly one that has a hydrogen on it. So this could be preferably something like water. We'll see why in just a minute why water is important. But what we're looking for is a nucleophile. Now, these CX3 groups are going to do two things. One, they're going to make this carbonyl incredibly positive because they're sucking a lot of electron density off of this organic compound. The second is that they're going to make this CX3 group very, very labile. Now, we talked about earlier reactions with carboxylic acid derivatives. This sort of looks like a carboxylic acid derivative. And what's going to happen is that our nucleophile, particularly one that has lone pairs in the nucleophile itself, is going to attack the carbonyl, and the hydrogen is going to come off of this methyl group to give us an R, O, nucleophile plus CX3H. So a trihalogenated methane and a new complex. This is what is called the haloform reaction, specifically when we run in conditions where our nucleophile here is water. So if we add water, we're going to produce a carboxylic acid and the trihalogenated methane. The use of this is that we can use this as a diagnostic test for methyl adjacent ketones, again, especially if this R group here doesn't participate in the tautomerization reaction. So the haloform reaction is used to test for the presence of methyl groups adjacent to a ketone, and it uses this enol-enolate tautomerization in order to form the CX3H, so if we work with iodine, triiodomethane, and the formation of a carboxylic acid. And the nice thing is this is a gas. So if we run this reaction and we start seeing a gas bubble out, we know that the organic compound we're working with here has a methyl group adjacent to a ketone.